Hey, Math 1050. Mrs. Bricky here. This is section 6.1 and 6.2, a total of 3 topics. So a matrix is a rectangular array of elements. It kind of is a bit like a little spreadsheet. And one of the things that a matrix can be used for is solving a system of linear equations, like we have been working with in chapter 5. So in order to use a matrix to solve a system of equations, we create what's called an augmented matrix. So for our system here, we take the coefficients from the equation and we put them in a row. So there's 0z there. So that first row in the matrix represents that first equation. And in your matrix, you have a column for the x coefficients, a column for the y coefficients, and a column for the z coefficients. And then your last column is what that is equal to. So the 5 here is in this last column. And sometimes you'll see a bar going down like this, and sometimes you won't see that. It just kind of depends. Some people always put it and some people never put it. So you may or may not see a bar like that separating the coefficients from the answers. And then the next row down would just represent that second equation. So we've got a 1 first for the 1x, a -1, and a 3, and those added together give us 1, so we have a 1 here. And then the last equation is the last row, 2, 1, 1, and that's equal to 4. So if you have the line there, the line is like the equal sign. We can use an augmented matrix like this to find the solution to the system of equations. So because this augmented matrix is representing a system of equations, we have several things that we can do to modify or manipulate that matrix. So first of all, remember that in a system of equations, sometimes we like switch the order of the equations, or that's definitely something we can do. If I switch the two equations, the system would have exactly the same answer. And so we can do that in a matrix as well. So this little notation here is saying to switch or interchange row 1 and row 2. So I can just put that row on top and that row on the bottom, and that is fine to do. It's one of our elementary row operations that are okay. It's also fine if you multiply one of the rows by a non-zero constant. That's just like taking one of your equations and multiplying it by 3. So that's absolutely okay. So in this matrix example over here, we have 3 times row 1 is mapping to row 1. So we're replacing row 1 with 3 times row 1. So you can see it turned into 3, 6, and 15. And that's totally fine to do. You can do that when you're using a matrix to solve a system of equations. And then remember, when we're solving a system of equations, sometimes we multiply one of the equations and then add the equations together to get an elimination or something. We can do that with elementary row operations on a matrix as well. So this is saying take 3 times row 1 and add it to row 2, and that's going to map to row 2. So you can see that row 2 changed, and what we did is 3 times this plus this to get 0, 3 times 2 minus 5 to get 1, and 3 times 15 3 times 5 is 15, and then if we add the -13, we get 2. Now, one thing to keep or be aware of when we're doing elementary row operations to manipulate a matrix is that you should only change one row at a time. So you can see, like on this one, we switched the 2 rows, so their position changed, but they didn't change. On this one, we only changed that first row. The second row stayed the same. And on this one, we only changed the second row. The first row stayed the same. So only want to change one row at a time. So when you're going to add a constant multiple of one row to another row, make sure you are only changing one row. So we're going to practice that just doing an elementary row operation. And then we'll talk about why we want to do elementary row operations. So we've got a matrix here, and we want to do -2 times row 2 and add row 3, and that's going to be changing row 3. So first thing is, we're not changing row 1, so I'm going to write row 1 down. I'm also not changing row 2, so I'm going to write row 2 down. The only one that's changing is row 3. We want to do -2 times row 2 plus row 3. -2 times this plus this. -2 times this plus the bottom row. -2 times 1 plus 2 gives me 0. -2 times 4 plus 0 gives me -8. -2 times -1 is +2. -3 is -1. -2 times 9 is -18, and we want to add -8, so that's -26. So a lot of times you could just like type this in your calculator if you don't want to be doing them in your head, with each element, but otherwise a lot of times you can just do it in your head to get that new row. So this is our new augmented matrix. So the purpose of doing these elementary row operations is to try to get your matrix into a form like this. So you can see on that last one we did, one of the results of our operation was that we got a 0 right there. And so you can keep manipulating the matrix and doing additional row operations until you get it into this form where you have 1 0 0 1 or like this. So the goal is to have zeros on each side of a diagonal that is a 1. Sometimes you'll end up with a situation like this, so we'll talk about that. But the reason that this row echelon form is what we want to get is because the row echelon form of a matrix, the reduced row echelon form, gives you the answer. Remember, this column was X, and this column was Y, and this column was the answer. So this top row tells me X equals -27. That's X plus 0Y. And then the second row down gives me the equation Y equals 6. So by doing row operations, we can get the solution. So that works with the 3x3 system as well. That first row tells me that X is 150. The second row tells me Y is -85. And the third row tells me that Z is 12. So that matrix gives me the solution to the system. And the process of like starting with the matrix that you started with and getting it into reduced row echelon form, that is called Gauss-Jordan elimination. This last matrix is a representation of a system that has infinite solutions. So if you think about that bottom row, that's saying 0x plus 0y plus 0, z is equal to 0. That's saying 0 equals 0, and that's true. So this is a system with infinite solutions, and we'll talk about how to write our answer in a minute. So the first two topics that you will have to do are guided Gauss-Jordan eliminations on a 2x2 system. That's kind of a lot to digest, huh? So it will show you on your screen, this process of starting with a system and using matrices to get to your final answer. It is guided every time, so you will just be filling in the boxes and the elements of the matrix. So I'm going to try to show this the whole time. So the first thing you'll have to do is augment the matrix. So you're just going to grab those coefficients or those constants and fill them into your matrix. So our first row is going to be 7, 21, negative 42, and then 4, 13, negative 29. Okay, so then it has 4 steps shown, and it will show sort of what your goal was on the matrix. So our first step is to get a 1 in that row 1 position. Well, that means I need to look at that position in the prior matrix. Right now it has a 7, and I need to multiply by some number so that I get a 1 there. So that number that I need to multiply is 1/7. Maybe you were thinking divide by 7, but that's the same as multiplying by 1/7. So we're going to do 1/7 times row 1, and we're changing row 1. So the first position, 7 times 1/7 is 1, and that was filled in for us. The next element is going to be 21 times 1/7, so that gives us a 3. And that last position is a negative 42, so if we times that by 1/7, we get negative 6. Now remember, we only change one row at a time, so the bottom row is going to stay the same. Okay, our next step, the thing that is changing that we're trying to get is that we need to get this 0 right here. We're only changing row 2. So I'm going to fill in row 1 because row 1 is not going to change from the previous step. Only row 2 is changing. So we need to multiply row 1 by something and add it to row 2 to get our new row 2. So if I look up here, if I'm trying to get a 0 in this position, I need to do negative 4 times row 1 and then add it. So this is going to be timesing by negative 4. Okay, so we need to do that for every column. So negative 4 times 1 plus 4 is 0. That one's already filled in. Negative 4 times 3 gives me negative 12, and then I'm adding row 2, so that's adding 13. So that's a 1. And then negative 4 times negative 6, and we're adding negative 29. So that's positive 24 minus 29. So that's negative 5. Okay, so we've finished step 2. If I look at step 3, the thing that I need is a 1 right here. So I need to multiply row 2 by something in order to get row 2, this new row 2 with a 1 in this position. Well, if I look at that prior spot on the matrix, it is a 1. So the number that I need to multiply is 1. I include this because oftentimes people see what they need to multiply just fine if it's a non-1 number, but then they get confused if they have to multiply by 1. But it is possible because of how this is set up as a guided elimination. So you do sometimes have to just put a 1 there. So we're just going to times row 2 by 1 to get our new row 2. So it essentially is the same. Our row 1 is also the same. We are not changing row 1. Okay, for the last step, we are trying to get that 0 above the diagonal. So if I look here, I need to times row 2 by something and add row 1, and the row that we're changing is row 1. Row 2 is not changing, so I can go ahead and fill this in. Okay, so the thing I want to times by is I need to times this by a negative 3 in order to add those two and get a 0. So negative 3. So negative 3 times 0, if I think about this first column and make sure this 1 stays what it is, negative 3 times 0 is 0, so if I add 1, it is still a 1. Negative 3 times 1 is negative 3, and if I add 3, I get 0. Negative 3 times negative 5 plus negative 6 gives me 15 minus 6, so that gives me a 9 in that last spot. So I've got the Gauss-Jordan elimination completed now in those 4 steps. And so now remember, this is our X column and our Y column. So this is saying X equals 9 and Y equals negative 5. Okay, so I think that actually is you'll have two topics that are similar to that. You won't have to do a 3 by 3 system of Gauss-Jordan elimination for any of your topics, but what the next topic is that you have to write the solution based on the Gauss-Jordan elimination. And then in section 6.4, you have to do something very similar to Gauss-Jordan elimination. So I'm going to show you how to solve this 3 by 3 system, but you will not have to do this as one of your topics this week. But it's good to sort of see how that process works with a 3 by 3 system. Whoops, that's a 1. So I'm augmenting my matrix. Sometimes I just want to write the variables. Sorry. -1, 2, 1, 2, 10. So I have my matrix augmented. I don't usually put the bar when I'm doing this, but you can put that if you like. And unless you've practiced this a lot, sometimes it can be hard to see what to do. And there isn't just one path. There's more than one path you could take. So what our goal is to get zeros down here as we're getting ones on the diagonal. And then after we have the zeros and ones, then we'll do this upper zero triangle last. So I already have a 1 in this position right here, and that's really kind of what you want first. So now what I'm going to do is try to get a 0 right below. So my goal is to get a 0 right there. In that highlighted spot. So the row operation I'm going to do is I'm just going to take row 2 and subtract row 1 and change row 2 is the one that's changing. So sometimes it's a good idea to write the rows that aren't changing in so that you don't accidentally start changing too many things. The only row I'm changing is that middle row, row 2. So I'm going to go ahead and write row 1 and row 3. And now I can do my operation to get row 2. So I'm doing row 2 minus row 1. 1 minus 0 gives me 0. -2 minus 3 gives me -5. And -1 minus 1 gives me -2. -6 minus 10 gives me -16. Sometimes people will say that your next step is to get a 1 here, but I prefer not to do that, especially if I can see that that's going to give me a fraction. So to get a 1 here, I would have to divide by -5, which would give me 2/5 here. I try to avoid fractions at all costs when I'm working with matrices because they just introduce a whole other element of possible errors to the situation. Okay, so my next goal is going to be to get a 0 here. So to get a 0 here, I'm going to add -2 times row 1 to row 3, changing row 3 only. So I'm going to write in row 1 and row 2 because those two are not changing. And now we can change row 3. So if I do -2 times 1 plus 2, that gives me 0. That was my goal. Now I just have to do that with all the other columns. -2 times 3 is -6, plus 1 is -5. -2 times 1 is -2, plus 2 is 0. -2 times 10 is -20. Plus 10 gives me -10. Okay, so again, it's hard to sort of get to the point where you can see a good next step, but what I'm noticing is that I have 5s here, and that looks nice to me because I can do an elimination and get a 0. But I also notice this 0 right here. And remember, the goal is to get it so that it looks like this with, my answers right here. So having a 0 and a number and a 0 is is what the middle row wants to look like. So I'm going to do two things here. First of all, I'm going to times this whole row by -1. And the reason I do that is because they're both negative and it's a good thing to do. So now I have a 5, a positive 5, and a positive 10. And now the change that I'm going to make to the matrix is that I'm just going to switch row 2 and row 3 so that this row is the middle row. So not changing anything else, just switching row 2 and row 3. So row 1 stays exactly the same. Row 2 becomes 0, 5, 0, 10, and row 3 becomes 0, -5, -2, -16. Okay, so we just switched those two rows. When you're switching rows, I would just be very, double check it, because a lot of times people will make a little error there. Okay, so now the thing I want as my goal is I'm trying to get this like bottom triangle of zeros. So my goal now is to get a 0 here, which is not going to be too bad because I have that positive 5 right above it. So my goal is to get a 0 in that green spot. So to get that 0, I'm just going to add row 2 and row 3 together, mapping it to row 3 as the one I want to change. So top row stays the same, middle row stays the same, bottom row, I'm adding row 2 and row 3. 0 plus 0 is 0, 5 plus -5 is 0, 0 plus -2 is -2, and 10 plus -16 is -6. And really, it was kind of a lot of work to get to this point, but once you get to this point, it is going to finish up pretty quickly. So you might notice, looking at this, that both of these rows are very easy to get a 1 in. So our goal might be now to get a 1 here and a 1 here. I can divide this row or multiply this row by 1/5 or divide by 5, and I can divide this row by -2. And I know I say only change one row at a time, but for something like this, I think it's fine to change 2 rows at a time once you're, more familiar with matrices. So I'm dividing that middle row by 5, so I get 0, 1, 0, 2, and I'm dividing that bottom row by -2, so I get 0, 0, 1, 3. Okay, so we're almost to our answer. You can see right now that y is 2 and that z is 3. We just need to figure out x. So the row operations I'm going to do now are, I need to do 2. My goal right now is to get a 0 here. So I'm going to do -3 times row 2 plus row 1. And we're changing row 1. So row 2 is not going to change, and row 3 is not going to change. Okay, so -3 times row 2 plus row 1. -3 times 0 plus 1 is 1. -3 times 1 plus 3 is 0. -3 times 0 is 0, plus 1 is 1. And -3 times 2 is -6, plus 10 is 4. And then finally, I'm going to try to get a 0 here. So my row operation is that I'm going to do row 1 minus row 3, and I'm changing row 1. So row 2 is not changing, row 3 is not changing, and row 1 minus row 3 gives me 1 minus 0, 0 minus 0, 1 minus 1. Oh my gosh, sorry. I wrote not what I said. This was 0 minus 0, so it was 0. And then lastly, 4 minus 3 is 1. So now I have my reduced row echelon form. We are finished, and our solution is x equals 1, y equals 2, and z equals 3. Okay, so again, you won't have to do any of those, but you will have to do something similar in day 4, which is why I was demoing it. So what your topic is it's going to give you this sort of last matrix, and you have to write what the solution to the system is. So this matrix is perfectly in reduced row echelon form. We've got that bottom triangle of zeros. We've got that top triangle of zeros. We've got our ones on the diagonal. So our solution, that top row tells me x is 1. Middle row tells me that y is 8. Bottom row tells me that z is -6. So you would just type those in as the solution. So if you have that reduced row echelon form, then the system has a unique solution and you can type it in. This is an example of a matrix where the system has no solution. So if you think about that bottom equation that says that 0x plus 0y plus 0z is equal to 1, but 0 is not equal to 1, so this system has no solution. So if you see a row like this where you have 0 on one side and 1 on the other, or any number here, that's no solution. And then the third possibility is something like this. So this bottom row tells me that 0x plus 0y plus 0z is equal to 0, and that is a true equation. So we have infinite solutions. So then you want to look at your other two equations. So one of my equations, that top row, tells me that x plus 6y is equal to 1. And the middle row tells me that z is equal to 6. So I'm not going to use this one because I know z is 6. So I need to be able to put a 6 there. You could, in theory, use either of those two to report your answer. Remember when we were solving systems that have infinite solutions, we want to report our answer in only one variable. So I would look at the other equation I have and I would try to see which one is the easiest to solve for. In this case, I think the x is easiest to solve for. So if we subtract 6y, we get x equals 1 minus 6y. And this is what I want to put in for x. So I'm going to choose this option, and it's going to be 1 minus 6y, y in the middle, and then z is 6. Now, it's also possible that you'll have something like with a y in all of the spots. We had some systems like that. It's also possible that you might have chosen to solve for y. So if you wanted to use x in your answer, you would have just solved for y, equals 1. So if I solve for y, I get 6y equals 1 minus x. I divide by 6, and this would go in that middle spot because that is what y is. So this would be an okay answer, and then this would be an okay answer. So it could be either of those. Okay, so that is it for 6.1 and 6.2. So let me know if you have any questions. These topics are due on Sunday. Thank you.